Hello and welcome everyone. We used to build programs with our shell, but let's see how it's done in GNU Guix. Today we will learn how to define packages, what build systems are, and why they exist, and we'll get our hands dirty and explore packages and build systems of GNU Guix. Hello everyone. Hello Rostislav, Alexander, Boring Beer Talk, Demis. Nice to see you. Let me switch the screen to my notes. Here is a simple definition, package definition, which you can find in manual and probably on many resources in the internet. Here we see a list of models that required to get some variables and functions from them. And here you see simple package definition. It's quite straightforward and probably understandable by even people without prior programming knowledge. But let's go through the fields of the package record. Here we call a package constructor and specify a few fields: name, version, source. Name and version basically strings, and I think they're obvious. Source is a little more complicated. It accepts a file-like object, and in our case it's a region, and the region defines some procedure that will obtain sources from remote source, and we also want to make sure that the source didn't change on a remote host, so we also provide a hash to be sure that everyone who builds this package definition gets the same sources and the build result probably will be the same. After that, the most important and probably most interesting thing in package definition is build system. And today we will explore a few of them and we'll see how they defined and how they works. Arguments. Arguments is something that helps to customize build process without actually modifying build process. And we'll talk about it a little later. And the few more things related to the information about package, like synopsis, description, homepage, and license, is also straightforward and obvious. The license is not a string comparing to other information fields, but an object which is defined in Guix licenses model, and you can find a lot of licenses defined here, and you can use any of them in package definition. The last field that is not covered yet is inputs. There are a few different type of inputs. Probably you will see inputs, native inputs, and propagated inputs. And let's talk a little about them to remove the confusion that usually exists. Inputs is something that will be built for the target platform. You know that Guix package manager can build packages for different platforms. For example, you are using x86-64 platform, but built for ARM. And inputs will be built for target architecture, in this case for ARM architecture. Native inputs is something that will be used for host architecture. For example, it may be some build utilities that not needed in runtime. It can be make utilities, some compilers, and so on. And usually in native inputs you specify some build time utilities that won't be used during the runtime of the application you're packaging. On the other hand, basic inputs can be referenced by the package. For example, you can specify in inputs some library that will be built for target architecture, and this library will be used inside the final binary of your program. And that is why you don't want to specify libraries in native inputs in most cases. The propagated inputs is similar to inputs, but inputs provided to the package won't be installed in the profile where you install your package, and only if they're referenced by the program, they will be stored in GNU store. But propagated inputs will be installed in the same profile where you install your package. It can be useful, for example, for Emacs. In Emacs, you want to load packages. You want to refer to EL files in some packages, and that is why in most cases Emacs packages adds the dependencies to propagated packages to be available in the same profile. And the same story for Python and some other languages. They want to be the dependencies available in the same profile. And the way those packages are found by Python and other utilities like Emacs is by using search passes or environment variables. For example, Emacs load pass or Python something Python library or something like that, which specifies the directory of the profile where those packages installed, and those propagated inputs became available for other packages and for Python and your package that's defined by you. And all of this called direct inputs because they're specified explicitly in your package definition, but there is something called implicit inputs. Those inputs are provided by build system. For example, when you use GNU build system, you will have make utilities probably Tools and some other packages added automatically to your package inputs. But as you can see here, in the inputs of hello package, we specified only gavk, but no make or Tools specified here. And development inputs is basically all of those inputs. It's necessary for things like nix-shell. If you want to develop a package and build it, you just get the development inputs of your package, and you get the environment where you have all build tools necessary and can do some manual operations in your shell and check if it builds or do some other things. And that's basically it about inputs. And let's go to the most interesting part of our talk, to build systems. What build systems are and why they exist. Basically, build systems is a number of build phases which combined in the list and executed sequentially. Those build phases can be customized by using arguments, and also some build phases can provide implicit inputs, which is usually required for all the packages that use this build system. And also they provide some useful utilities. For example, Emacs build system provides some wrappers that allows to execute as expressions using Emacs to build something or to produce some output which will be used in the build time. Any questions so far? We will explore a few of build systems, and we'll start from trivial build system, which probably the most simple of them. And we'll start from Guix source code, from Guix build system trivial model, and we'll just explore it. Here you see a few things, and one of them is the function lower, which returns a bag. Bag is low-level representation of the package, which will be later translated to the derivation, which will be built by build daemon. And here you can see that how some parts of the package record will be translated to the back record. It's more technical details and probably not very interesting for our today topic. We will take a look at more high-level details. Here we can see the trivial build function, and we see that it accepts name, inputs, outputs, and a few more parameters. The most interesting parameter for us is builder, and a little less but still important parameter is models. Builder is basically a list of expressions that will be used to build the package. Also, builder can be a G expression. What is G expression? We already discussed a few streams ago, or maybe many streams ago, but we will recap, or maybe we'll make a small introduction today to G expressions. But for now, let's imagine that builder just a list of expressions that will be used during the build phase. In comparison to our usual build process, when we type commands in our shell, in Guix we use a scheme language, GNU-GUIL, for describing our build process, and that is why we use S expressions or G expressions for describing our build process. And in a few minutes we will see how we define it and how we use it. And here you can see that if builder is a list of expressions, then we translate S expressions to G expression. And otherwise we use builder as it is, and probably that means that the builder is already a G expression. After that, we create a derivation, and our build procedure will look like a builder with few additional definitions. With build variables, a simple function which just adds three variables, which will be available in the build expressions: build inputs, outputs, and output. It's actually done for backward compatibility. Right now we already can describe a build process without using those variables, but it's still available here. Okay, here we saw how some parameters of the packages went to more low-level representation, which will be used for our build process. But now let's see how we can customize our build process by changing package definition. And here I copied a simple epipe package from Emacs XYZ model and slightly customized it. Here you can see usual definition of a region, which just downloads the Git repository, and later this Git repository will be operated during the build process. We set build system to trivial build system, which the definition of which we already saw, and we set a few arguments. Those arguments allows to customize the build process. Actually, it is required to set a builder argument for trivial build system. For other build systems, sometimes it's not even necessary to set arguments, but today we want to explore and touch them, so we'll be trying to modify and explore as much as possible. And here the first argument is models. It's something that will be available for our builder, and our builder just a list of expressions that will be evaluated on our build machine by build daemon. And if we comment out the models argument, and inside our build expression we'll call format. Format is just basically a thing that allows to print formatted strings or return a formatted string as a string. But in our case, it will print because of first argument. And let's use this command to build our package, and we'll see the result. Actually, what we print here is a list of models that available in our builder. And here you can see that Guile, system-based compile, and that's all. Only 2 models available for our build expressions. But let's enable models argument and specify Guix build utils. I will explain later what this model contains. But for now, let's just see how the list of available models changed here. Available models still the same, but if we add use model definition, we should see that one more model appeared here. Very cool. That means that we can provide additional utilities or some scheme code to our build process by using models argument for trivial build system. Actually, we can see how it's implemented in trivial build system, and let's see models. We see here that G-expression to derivation function accepts a keyword argument called models, and we provide just a list of models to it. But as you can see here, we use G-expression as a builder. That means that we can use a special function called with imported models. With imported models, which will allow to do the same thing, but without specifying models argument. Of course, it's not necessary to do this thing this way, but I just show the possibilities and probably the customizability of build systems and G-expressions. As you can see, it's successfully built and everything works fine. But if we will comment out this line and this line, we should get a build error. Okay, as expected, we get an error, and this because the model is not available. But as you can see, we can provide models the both ways. Attach it to G-expression, which will be serialized and executed on build daemon, and by using models argument. Demis says that he will rewatch the stream and gotta continue working. See you later, Demis. Always a pleasure to see you on streams or mailing lists. Okay, we saw that there are a few ways to provide models to our build script, to our build expressions. Let's see what is inside Guix build utils. Guix build utils is basically a list of functions that can be used across many different build systems and build scenarios. It defines various predicates, for example, checking file types. It defines some helper functions like make directory, install files, change file permissions, copy, delete files, find files by regular expression or some predicate, and many others. Invoking some custom programs, setting environment variables, creating wrappers, and intermediate files that can be used later. And this namespace, this model doesn't have external dependencies on other models of GNU Guix. That is why it's quite simple and easy to add to build time dependencies. And most build scenarios can be accomplished with the usage of those functions. For example, you can create directory with make dir, change directory with change dir, copy all the files using copy recursively function, update the file content, changing some hard-coded values to the passes in the store using substitute and patch functions, and install files to the output directory with install file and a few scheme constructions like for each and string append. But some build scenarios is a little more complicated. That is why other build systems exist that contains a little more helpers which are specific for those build utilities. Let's take a look at GNU build system. Its definition a little more complicated than trivial build system, but basically what we want to see here is that it adds some dependencies. Let me find the place. It's here. It adds some dependencies that are required for GNU build system, and probably the list of packages that will be added to those dependencies is afterconf, aftermake, libtool, gettext, and techinfo. The actual build phases are defined in a different place. Here you will see the arguments that can be used for customizing build process. Let's find them. Here a list of things that will be used later in our build phases is for example tests and test target. It's a make target which will be used to run tests. Test controls if we want to run tests or they should be disabled. Parallel build and parallel tests controls -g argument for make, which of course runs tests and builds in parallel, and a few more arguments that will be used in the build phases. And let's see oops. Let's take a look at GNU build system file. This GNU build system file contains a lot of build phases that will be available and used during the build process of the package. We can go through them, but let's go to the definition of the variable called standard phases. And this standard phases contains a list of pairs, and each pair is the name of phase and the actually function which implements this phase. Here used a special macros for defining those pairs. You can see it takes the phase name and creates a pair of this phase name and actually the function with this name. And we can see the implementation of those phases. For example, let's see the unpack phase. Unpack phase creates a source directory, goes into it, and copy recursively everything from the source argument to this directory. After that, it makes every file in this build source directory writable, and also there are some conditions related to archives. If our source is actually a zip or tar archive, they will be extracted. And that's basically it about unpack phase. If we take a look at our example package using a trivial build system, we will see that we have something similar. We have a copy recursively call with change directory call. And in more complicated packages, it's very usual step during the build process. That is why, for example, GNU build package has this unpack phase, which works this way. For some other build systems, it can vary, of course, because the source code for those build systems may be organized a different way or maybe have some specifics, but the idea is still the same. After that, you can see that in our example, we use a construction which calls for each file here install file function. And if we take at install phase at GNU build system, we will see here a different thing. This thing just calls make install with make flags. Make flags provided using arguments of the package. And it's the install phase which usually you will see in GNU build system, because most projects using GNU build system have something like this in their workflow, which we usually call from our shell, but in our Guix package definition, it should be described in scheme language, of course. And this is an install phase described in scheme. But if we will go through this code, probably we will see install file call, which is inside licenses files, which probably it's quite long function, and I don't want to dive too much into it. But basically what it does, it's probably copies some files to the build folder, to the folder with the build result, using copy recursively and install file functions. Here we see the transition from our trivial build system to GNU build system when the projects are more complicated and requires more build tools. It makes sense to extract the patterns which frequently used and wrap them into these build systems, which consist of build phases which can be customized with the arguments. And let's take a look at another package. It will be orderless, for example. This package uses Emacs build system, and let's build it. And we can see the result of the build for this package. This is a shared directory which contains doc directory with license Emacs directory with Lisp and Lisp compiled files, and info directory with the manual. In comparison to trivial build system, we don't see any code that generates our elisp and elisp-c files. That is why it is because those phases defined inside Emacs build systems and applied for all the packages using this build system. But here we see the customization of build process. It's done using arguments, and here in arguments we set phases to the expression which will be evaluated during build time. To make it clear that this expression is evaluated during build time, we make it a G expression. Oops. All G expressions usually always evaluated on the build side, and if you see that it's a G expression, you can be almost sure that it will be evaluated by the build daemon. What happens here? Here we set phases argument for our build system, and if we open Emacs build system file and we'll see how Emacs build function defined, we will see that it by default contains a phase keyword argument equal to standard phases. And here it returns a builder, basically the same thing that we defined in trivial build system, but here it's a little more complicated, which calls Emacs build with phases set to phases provided by argument. Let's see where our standard phases for Emacs build system is defined. Here you see in Emacs build system SCM the definition of standard phases, and it's actually not something that's done from the ground up. It's just a GNU standard phases, but slightly modified. Using modify phases macros, we take a list of standard phases for GNU build system, replace unpack with different implementation. Here it's a little simpler. Actually, it's a wrapper that in case of one file, one EL file, do create a directory, goes into this directory and copies this file to it. And in other case, it calls GNU unpack. We can say that Emacs build system inherits GNU build system and builds upon it. Can Emacs build system zip elisp files? Yes, of course. Actually, you can see it compress the documentation phase. It should be here. wait a second. It's probably not here. It's probably in GNU build system. Yep. In GNU build system, we have compressed documentation phase, which basically takes info files and gzip them. So you can see the example of zipping files here. But despite the fact that Emacs build system can gzip Lisp files, it doesn't do it. But theoretically it can. Okay, we talked about inheritance of standard phases from GNU build system, and here you can see that we applies some changes to this list. After unpack, we also add expand load path. Actually, the build systems not only build projects, but also prepare the environment for building of this project by setting necessary environment variables, for example. And this is one of the examples of such actions. Okay, we can see all the modification to standard phases of GNU build system done by Emacs build system, and let's rebuild the package, Emacs orderless package, to see all the phases that is done during the build. Here in the log, in the output, you can see that here we see starting phase, blah blah blah, and we can see that there are a lot of phases. And those phases, some of them comes from Emacs build system, and some of them comes from GNU build system. For example, compressed documentation is not defined in Emacs build system. It's defined in GNU build system, and it's inherited here. Okay, let's go to the package definition, and let's try to customize it somehow. We see that for our J expression, standard phases is available, and we can modify it, and after that the value of modified phases will appear in Emacs build system. And let's just comment it out and see that it will disappear from the list of phases that we saw in the log, in the build log of the package. You can see after install we have make after loads, when previously we had make info phase. To be sure, let's restart the build one more time and see that this phase appears. And here we see after install we have make info phase, which is kind of expected. The question was what variables are available in our build expressions. This is a good question that I asked myself. and we can find out the answer. Here you can see the Emacs build system models, and those models will be available to our build expressions, and we can see where they used. They by default used in imported models argument, and if we see where our imported models argument used, imported models argument used, we will see the same pattern that we used in trivial build system when we used with imported models and wrap our G expression with this function. The same thing used in Emacs build system. That means that all models defined in imported models will be available for our build expressions. That means that we can customize in our argument list imported models and set it to something like Guix build utils or something like that. But before that, let's go back here, and here we see that GNU build system models added here as well, and we see that GNU build system models already contains Guix build utils, Guix build gremlin, Guix build GNU build system, and Guix elf. What else we can add here to demonstrate how it works? Actually, we can just override. We can override a list of imported models and let it fail. We set imported models to only Emacs related models, and probably it will fail because invoke, install file, and so on won't be defined because there is no Guix build utils here. Okay, we see that there is no code for model Guix build GNU build system. It comes from here, I suppose, or not? Okay, whatever, let's add this model, GNU build system. Oh, it comes from some phases that probably use some code from GNU build system. And now it will fail with build gremlin. Oops. As you can see, we add one by one the same models that are defined in both Emacs models and GNU build system models. Here you can see how changes model import compiled, derivation and new models added here. And it still fails because Guix build utils not yet added to the list of imported models. Nice, it was built. And let's set another flag. For example, tests, which is used, which is defined by GNU build system, but also used by Emacs build system. Emacs tests. And by default, it's set to false because many Emacs packages probably don't have tests. And we will set it to the true, for example. And let's see what will happen. And of course it will fail because GNU build system, the part that comes from GNU build system, which do check phase, will call make check -j for parallel tests, and it of course will fail because this project doesn't contain makefile. And we can set parallel tests to false. And we will see slightly different errors. Now we don't have -j argument because parallel tests is false. The interesting thing is that here we can use display hello from G expression instead of value. We probably can use a G expression, and inside this G expression we can do some magic, and in our case it will be just a printing a line. You see this hello from G expression. That means that we passed to tests not just boolean value, but a G expression which will be evaluated to the boolean value. Okay, we actually talked a lot about different technical details, but I forgot to talk about the phases themselves. The phases basically a function which accepts a list of keyword arguments and launches some actions. Here a simple example of modification of build phases. We take standard build phases from Emacs build system and add another build phase called makeinfo. And this build phase is described by a simple lambda function which accepts only one argument, keyword argument called outputs, and ignores all other keyword arguments. And after that just invokes makeinfo on orderless tehe file and install resulting info file to the output directory to the share info of output directory. Um, this is very useful when your build process or build process for some package differs from usual build process of this build system only slightly. In our example, it just adds another step where we build info file and also install it, but this is a very good example of modification of build process. We have the whole build process already defined by a build system and reuse all the stuff declared in it, but also add a small step which modifies the build process, and it's very flexible and hackable. As you can see here, the whole power of full-fledged Lisp language available for us to define the build process, and many build processes already defined by different build systems. If we take a look at Guix build namespace, we will see a lot of build systems already defined that we can use, and if some of those build system doesn't work for us, we can modify the build process of this build system or create a completely new one. I also wanted to cover copy build system, which quite simple and allows to just take files that provided in source of the package definition and put them in some output directory. But in the manual it's described quite well, and also you can see the source code and the examples. It just accepts a few arguments like include regex, exclude, and you define patterns by which those files will be installed in your system. And that's it. We can take a look at the example of copy build system usage. Here we define install plan, which says to install ls binary to bin directory, docs ls info to share info directory, and ls org to share docs ls version directory, and that's it. Quite simple. Hi, John Smith. The master is playing his instrument. Okay, let's go back to the notes and see if I missed something or not. Build system utils. Let's take a look at Emacs utils example. Here in an additional namespace, which is available build time for every package which uses Emacs build system. And it's just a list of helper functions like Emacs batch eval or Emacs batch script, Also byte compile directory, generate afterloads, and substitute as expressions and variables. So in every package definition using Emacs build system, you can modify phases, and inside those phases, all those functions will be available. And the documentation for those functions is also available in docstrings, which you can find here. And the implementation is quite simple, so in most cases you can figure it out even without documentation. Okay, for many languages, programming languages, they separate build phases, of course. We already see the whole list of them. And a few more you can define yourself. Some repositories of software which contains Guix packages also defines their phases for different use cases. We talked about phases and arguments and how to use arguments to customize phases and the whole build process. We talked about models and imported models. Imported models is something that will be added to your build expressions and will be available build time. And models is something that you also can define in arguments, and it will be added to use models definition, which will require necessary models for your build expressions automatically. But you can define use models inside build expressions yourself. And different build systems can have different arguments, so it doesn't mean that every build system contains imported models and models arguments and maybe some other arguments. We talked about Guix build utils model, which contains a lot of useful things for manipulating files and do other stuff related to the build process. I advise you to explore it yourself to get familiar with it. Also, there are some other models that can be used for useful for package definitions. For example, Guix packages, of course, which contains some macros like modify inputs for easier manipulation of package definitions. And I think that's it for today that I wanted to cover. Maybe later we'll cover some more technical details. But for today, I think we already went through the main phases of the build process. And to recap a little, Guix describes build process in GNU-GUI, and the build systems are intended to simplify repetitive or frequent workflows and to extract some patterns that usually used in those build processes. And we have a GNU-GUI for describing those build processes, which absolutely hackable and amazing. And I advise you to experiment with package definitions and to learn more. And you will enjoy packaging software and making the build process more reproducible and repeatable. And I hope you will share your joy with the other people and the rest of the community. I hope you enjoyed today's talk. And as usual, make love and not war. See you in a bit.